Okay, now the next objective of this series of videos on synchronous counters is that one of inventing an internal architecture. And because we are using all the time this architecture based on finite state machines, we will do that in several ways, precisely as a plan X, later on as a plan Y, and finally as a plan C2, as if we were still organizing chips using smaller components. And this time, let's talk about the plan X, okay? Basically, it is all around using the finite state machine as usual, enumerating states. So you can develop the truth table of the circuit, the combinational circuit one as usual. You see, using labels for every state and trying to plan the next state to go the same way. Organizing all the loops and all the signal transitions, or all the transitions between states that way. Okay, so let me see now if I can explain you after the specifications of the circuit some ideas on planning the circuit as a finite state machine. You know that this is solved all the time the same way. We will develop the state diagram, transferring the function table and the symbol input and outputs to something like this. You see, a sequence of states, you name them in some way or another, state 0, state 1, state 2, state 3, state many more, state 8, state 9, and then again state 0. So depending on the input conditions, you see the values that you are sampling on the rising edge, depending on this, sample values that you are sampling from the control inputs, you can allow the system go advancing from one state to the next, or keep the state in a kind of a loop, you know, 0, 1, 1, 1, 1. You can repeat the state 1 as many times that you like. If you are sampling the containable equals 0, so you see, this is the meaning of this idea. Containable 0 means that the value sampled at the rising edge of the clock, okay? If at this time the containable is 0, for example, you like to repeat the current state in which you are. But if you are sampling a 1, because of this time, you know, when you have the rising edge, you like to go advancing. So there is this idea of a different BCD number per clock if you allow the system counting. And when then you are at 9, if you allow the system go counting, if the containable is held is high, you know, you keep counting, and TC10 is 1. So you have a pulse every 10 pulses in this way when counting continuously. So that is the circuit, the counter BCD. And you know that what goes next, for example, is imagine that this is simply another application of a finite state machine. So if you think that way, naturally this state diagram is not very much different from the one that you had in the traffic light controller, or the light control, or the lamp, flashing torch, you know. Any other idea that you have in mind, the clicking buttons, doesn't matter. Other examples generates similar state diagrams controlled by inputs or straight conditions depending on the clock only. So when you've got that, you can go to the next step, that is transferring this state diagram by means of a finite state machine into a circuit. So this time, you know, it is like this. The input, the control input goes to CC1 and CC2 because the TC10 depends as well on CE, you see, like here in this state. But you know, generally the inputs of the CC2 and the CC1 are nothing but the current state. The system is at 9, so the machine has to know what to do so that the next state is 0 or the 9, depending on the containable. So this is the truth table that is associated to the CC1 and the CC2. Generating the next state to go, or generating the full set of 5 outputs here. 4 of them organized as a binary combination, or a BCD combination from 0 to 9, and the other one just a single pulse every 10 states. That way. And you know that you have as well the state register that is connected like this. It's basically an array of data flip-flops, and the number of them depends on the way that you are. You see, you have a state here, so in which way you are encoding, and in which way you are encoding the labels of such states, in which way. For example, if I mean that if you are doing that in binary sequential, for example, in binary sequential, this means 0, 1, 2, 3, 4, 5, 6, and etc. etc. In binary sequential, or in gray, that is another binary code. In this type of encoding systems, or you simply need R equal 4 bits. This is what is required. You see, R is 4 bits is enough, because using 4 bits you can encode up to 16 states, and here you have only 10 of them. So from all the 16 combinations, there will be 6 of them left unused. So this is a possibility. The other possibility, for example, is use another code like the one hot. Okay, only one at a time asserted. So in this way you have 10 states, so you need 10 bits to save this situation. But in one way or another, this is what goes next. The state register implemented using an array of D flip-flops, 1 per bit, and depending on the encoding, you have here the memory of the system. So the current state, in some way or another, is keeping inside the machine this internal state. That means the label. You know, the machine knows in which label you are by means of a binary combination. So depending on the label you are generating the next, or depending on the label you are, and some external inputs, you generate the next state to go, you see? So what goes next, if this is the mechanics of the finite state machine, is to generate the truth table. Absolutely, you see? So if you have this idea, inventing this block, a combinational circuit, you better now organize here the truth table. So something like this, count enable and current state. Alright, so if this is what is the input of the system, you can generate the queues and the TC10, for example, in a single table or in 2 tables. That's not a problem. So if count enable is 0, for example, you see, if count enable is 0, if the current state, whatever it is, you see, whatever current state, now in the present, now, just now, the Q is the same. You see, the Q in the future is the same Q. You know, the Q is the same. It's not changing, you see. I mean that I can do that better, you see. So if this is S0 or S1 or S9, doesn't matter. The Q is you know that very well. 0, 0, 0, 0, 0, 0, 0, 1, and 1, 0, 0, 1. There is no need to go doing that in another way, you see? And if count enable is 0 for all these combinations and current states, the TC10 is 0 all the time. That is the way it goes, right? That is the specific table for this condition. Now you can very well imagine that if this is 1, now the system will count. So what? S0 and S1 and S9 is the same, 0, 0, 0, 0, and down to 1, 0, 0, 1, the same sequence of, or translations, you see, in some way. the current state is all the time translated to Q, so in some way this table is redundant. It's not necessary to do it, but the containable equal 1, yes, it is like that, 0, 0, and then 1. When containable is 1 and you are at the state 9, you have this one here. So you see, if you don't know how to do the table, well, let's try, because in the end it's, even if it's repeated, because now you can do something better here. You can take, you can imagine that the current state is what you need to set the Q simply, and in order to set the TC10, you see, it's a very basic function that has a single mean term, the number of which depends in the way that you are encoding the states. This is the advantage here. You see here in this place, when we talk about current state and next state, we do not use binary codes, because that may change depending on the code, and it's because it's more practical to use the label. Look at this. The label gives you a lot of information, and you can also build the truth table the same way. Okay, so if you have the truth table of the CC2, you see, so then what? If you have the truth table of the CC2 like this, you can very well now translate the table using the plan B as usual. So asking a question here, which is the value, for example, which is the value of the current state? Okay, and here you may say S0, S1, S2, S3, and up to, you see, you can go up to S9. So then what? If it happens that you are at S0, what is that you are going to do here? So just as operation, that means Q equals 0, 0, 0, 0, and TC10 equals 0. That's the operation. And that can go in a similar way up to S9. So in S9, you can fix the Q's if you like. Q equal 1, 0, 0, 1, because they are the same, you see. Doesn't matter the value of containable, but now you can ask a question here. Which is the value of containable? Is containable 1, for example? You may say yes or no. All right. If you say yes, well, so this time it means that TC10 happens to be 1. Okay, something like this. But if containable is 0, you will do this operation, TC10 equals 0, as in many other states and for all other circumstances. So this is a transformation of the truth table of the CC2 into a very simple flow chart. You see, practically subdivided in 10 different states, and this means that here you can use the case statement, and perhaps down there you can use the if and else. That way. So as you can imagine now, browsing the given BHDL file that is there for you to copy and adapt and study, you have to see in some way that the final implementation of the BHDL from this flowchart is not that difficult in the end, you see? You will find the entity and then the definitions, you know, of the state type, state, next state, and current state, state type, state enumeration, S0, S1, S2, and then, you know, the truth table CC2 translated to a flowchart, and finally to this BHDL sequence. And you can do exactly the same for the CC1, all right? No problem. Perhaps the CC1, because it's about implementing the arrows, is in some way even simpler. Well, this one is extremely simple, right? But you know, you can implement the other one in the same way. Let me just show it to you for some states, because you have the great advantage of using labels and being able to go one state at a time to the end. okay, like this. So now, if what is next is the implementation of the CC1 to table, well, the same kind of inputs that we had before, count enable and current state, okay, but now the output is not the 5 values that you will see, but nothing but an internal wire that is called next state to go. So very well. So look at this. The implementation is going and imagining state by state the arrows, right? Here you have 2 arrows to solve in a state 0. So why don't you do, well, that depends on the way you are organizing this, because you see you have all the arrows, all the loops repeated if count enable is 0. So you can do as you like, but you can generate a general if. For example, if count enable is 0, you may say that doesn't matter the current value. Whatever, the next state is the same. Current state. You see? The next state is the same current state that you have now. So with if count enable is 0, this implements, you see, all the loops. And now you can subdivide the table in 2 sections. That is the one section for all the 10 loops. So now what is left is the 10 translations of a state transition. So if this is 1, you see, if this is S0, the next state to go is this arrow, you see? This arrow. If count enable happens to be 1, you go to the next state S1. If now you are in S1, you go to S2, and all the time the same way to the end. S9, you see, S0. So that's the table. You see, that's simple. Tell me if this is not what you want. You see, the implementation of all the state transitions. Okay, every time that you have something in mind, remember that it's very important for you to go annotating what is happening here. What is that you try to explain? So that is a true table. So what goes next? As you can imagine, this is going to be, you see, this if is, you can talk directly like this. You see, if 0, else when 1, you see. So this is, this subdivision is very well translated using this plan B. Now, using the first question here, you see, what about count enable? You see, if count enable is 0, if you say yes, so what is that you have to do? What is that is left to do in this system? Well, you see, next state is simply current state. And that happens for all of them. So, you see, this is a kind of a general if. So, if yes, you do that. But if no, you see, if no, this is a kind of a else later in VHDL. What is going to happen in this else? Well, now is when you are going to solve this subsection of the table using the case statement. So now is when you ask for the current state, for example, okay? What kind of current state you have? Which is the level of this current state that you have? You see? S0, S1, S2, S9. So you see, depending on the current state, this is what is translated as a case, a structure. In the process, you see, plan B, using this process, you can very well assign here that current state, you see, happens to be S1. Or here, you see, current state is S2, because now you are in S1, and so on and so forth to the end. So here current state is just state 0. So in this way you are solving the flow chart that now is immediately translated to VHDL. Alright, So you see a counter, yes, but nothing but plan X, just another finite state machine as usual. The plan Y is very similar, it's just another finite state, it's slightly different because we will not code in one hot, for example, or in gray. We will code all the time in binary, so we will have another possibility for implementing the CC1 in addition to this one that is stated here in plan X. And then there is even another way to do counters, that is the plan C2, from which we will talk in another video. And the plan C2, as you can imagine, will consist on using a standard counter placed inside this device, so that using a standard counters and other components you'll be able to implement the one that you like, okay? So that is the video recording of this, because what goes next, it's that simple. You only have to find in the digsys webpage an example that resembles this, you see, this BHDL, and then go and develop and test so that the circuit works exactly as the one that you have for real in a standard chip 74160, or the model that you have in Proteus, or any other one that you may like to try in the lab.